In the second part of section 4.2 today, we're looking at third angles theorem in triangles, and we're going to do some proof today. What third angles theorem says is that if you have two angles of one triangle congruent to two angles of another triangle, then the third angles are blank. And I'm going to explain this a little bit, see if you can fill it in. Well, if I have these two angles being congruent to these two angles in this other triangle, what could I say about this third pair of angles that are supposedly unmarked here? Well, if you know these angles are congruent, let's just give an example. What if these were both 100 degrees? Looks like they're more than 90. And they'd have to be the same measure, right? They're more congruent. Let's say these are both 50 degrees. Again, they have to be congruent. Well, wait a second. Don't I know that the angles in a triangle add up to 180? So if this is 100 and this is 50, I'm at a total of 150. This has to be 30 no matter what. And same deal here, right? This has to be 30. Well, if you know two angles are congruent to these two angles, that remaining angle is going to be an exact specific number because we know the angles in a triangle have to add up to 180. So hopefully you can fill in the blank above for me here. If you know two angles in one triangle congruent to two angles in another, the third angles are also congruent. They have to be. So it's kind of neat. You don't really need all three angles congruent in a triangle. You only need two angles congruent in a triangle, and you automatically know that the third pair has to be. Find the measure of angle YXW. Where is that angle? YXW. Y to X to W. YXW. Actually, that's this entire angle, right? So I need that entire angle. Let's see here. I know this angle is marked as 40 degrees. It must be congruent to this one. This is marked as 35 degrees, this little one with two arcs, which must be the same here. Well, I guess I should focus on the correct triangle. This angle I want, YXW, if I highlight the angle I'm speaking of, I realize the only triangle that big angle is in is this triangle here. So that's a triangle I want to focus on, and I know this angle's 40 degrees. Do I know this angle? Oh wait, it has two arcs just like that guy. So this angle is also 35 degrees, which now I should be able to find my missing angle. I know the angles in a triangle add up to 180. Right now I have 40 and 35. So right now I have 75 degrees, so I'm going to take 180 minus 75. And I know that the measure of angle YXW then would have to be 105 degrees to add with those other two to be 180. Okay? So using a picture there and identifying some overlapping triangles and trying to figure out which triangle is actually talking about, using some congruent angle marks too. Here's a proof I was talking about. Let's see, what am I given? I notice nothing's marked in here, so I'm going to start marking what I am given. I'm given that line segment AD is congruent to line segment BC. So side AD congruent to side BC. I'll give those both one tick mark. I know that side CD is congruent to side AB. Line segment CD, two tick marks, congruent to line segment AB. Two tick marks there. Oh, sorry, this should be over here. Angle DAC. DAC. A is a vertex. This would be my angle. I'll put one arc. Is congruent to angle BCA. BCA. That'll also get one arc. Let's see. I also know that angle ACD is congruent to angle CAB. Angle ACD. Give that two arcs. Congruent to angle CAB. CAB. Add vertex A. There it is. Alright, I gotta prove that the triangles are congruent. The triangle ACD is congruent to triangle CAB. Looks like they wrote it in the correct order, right? ACD went along this shared one from one arc to two arcs, and CAB one arc to two arcs out here. Okay. Alright, let's do a two-column proof. We've been doing paragraphs quite a bit. We'll do two-column ones. Alright, remember to do statements and reasons as my headings for the column. Wow, I have a lot of givens, so that'll take a while. First thing I was given was that AD was congruent to BC. and CD is congruent to AB. Now I'm putting these in the same step only because they're both sides. I was given two side pairs that are congruent. But remember, if I want to prove that these triangles themselves are congruent, I'm going to need all three sides congruent that correspond, and all three angles congruent that correspond. So maybe now that I've done two of the sides, can you tell me why is the third pair of sides congruent? The only side that's not marked or talked about is right here. But actually, isn't this a part of both triangles? This side AC is in triangle ACD. This side AC is in triangle CAB. So in my next step, I'm actually going to say I know that side CA or AC is congruent to itself. And I know it seems silly to say something is congruent to itself. It seems obvious, but I have to say that CA is congruent to itself. And why do I know anything is congruent to itself? Because of reflexive property. Because if you look in the mirror, you see your own reflection. Sorry, remember reflexive property. And here it's reflexive property of congruency, since we're using congruent. At this point, look, I have all three sides congruent, so that's covered. Okay? Next thing I'll focus on is the angles. Now they gave me two angle pairs congruent, so I'll write those out. They told me angle DAC was congruent to angle BCA. They also gave me angle ACD was congruent to angle CAB. Given to me. And I marked those two angles. But if I want to prove that these triangles are congruent, I need all three pairs of angles to be congruent. And is that true? Hey, what did we just talk about earlier? If I know that two angles of one triangle are congruent to two angles of another, the third angles have to be congruent. Remember, it's because that these angles have to add up to 180, so the last remaining angle would have to be the same too. It's called third angles theorem. So when I go back here, the only angles I have left are angle D and angle B. By the way, I can name them with one letter because there is only one angle I could talk about at vertex D. Congruent to angle B. Again, only one vertex angle B, so I can use one letter there. But how do I know those angles are congruent? Because I had two angles congruent in these two triangles. The third pair has to be by third angles theorem. Kind of nice. You only need two angles congruent in two triangles, and you know the third pair has to be congruent. And at this point, now I have all of the angles marked congruent as well. Wait a second, all the sides are congruent. All the angles are congruent. Don't I know the triangles are congruent now? I can prove what I want to, that triangle ACD is congruent to triangle CAB. I'm using their proof statement, and how do I know that? I know it because all the sides were congruent and all the angles were congruent, and I know that to be congruent figures, that is the requirement I have to meet. This is actually the definition of congruent figures. I gave you this definition yesterday. To be congruent figures, you need all corresponding parts congruent, meaning angles and sides. And we have fulfilled that definition. So great proof today using that third angles theorem and actually using reflexive property, saying that anything is congruent to itself if it is a part of both figures. Alright, one more slide here. These reflexive, symmetric, and transitive properties are coming up again. All it's saying today is that they do hold or do work for congruency of triangles too. So reflexive property works for triangle congruency, meaning, remember reflexive was anything is like congruent or equal to itself. So I could say that triangle ABC is congruent to itself, triangle ABC. Remember symmetric property was, you think symmetry, so like sort of a flip over or a reverse of how it was written. So if you knew that triangle DEF was congruent to triangle GHI, then if I think symmetry of this, I could flip those around and do triangle GHI first, congruent to triangle DEF. And finally, with transitive property, remember transitive property, we kind of think like chain rule or terrain there. So if you have two things congruent to the same thing, they're congruent to each other. So if you knew that triangle RST is congruent to triangle VWX, and you also knew that triangle VWX was congruent to triangle YZA, and what's your last statement? We'll notice that we had triangle RST was congruent to this triangle VWX, and that same triangle VWX, was also congruent to triangle YZA. So my last statement is knowing that triangle RST would also be congruent to triangle YZA, seeing that they were both congruent to the same thing. So these properties also hold for triangles. A few more theorems today, and working with proof of triangles.